The talk will focus on the topic of how can we train stable diffusion models under $2,000. 2000 is sort of, I think I'll explain the sort of like the reasoning on how we ended up with this number. But overall, I hope that you'll read as or perceive it as that how do you train these models under a very low budget. I'll explain quantitative also in a minute. Most of us in the audience would agree that we have made a tremendous improvement in visual generative AI. For example, just 10 years ago, with the advent of GANs, we were struggling to just generate photorealistic images on a dataset like CFAR10. And today we can generate, with latest flux models, photorealistic images in a wide range of different scenarios. For example, here, a giant lizard attacked a man in China, and the image is highly photorealistic. But one of the key investment or one of the key hurdle behind training these models is that training them at scale is actually very expensive. And here I'm considering like even early sort of like these early stage models, the early version of stable diffusion models. Training them, it costed stability in close to $250,000 at that point. Often these models themselves were trained on billions of images, and that has also become a norm at this point. If one has to replicate the training of stable diffusion 1.5 and 2.1 today, it would still cost in order of $30,000 just for one training run to finish, or in other words, roughly 40 days on 8H100 GPUs that are commonly available in sort of like academic labs or small scale industry research labs. So the objective we had was, how can we build a setup? How can we build a test bed that can retain the similar performance of our large-scale diffusion models, but can drastically reduce the cost required to train them? And this is like a concrete setup we opted to follow. So here, as I was saying, we assume that the user or the researcher only have access to a modest amount of compute. And some of these constraints actually were informed by what, as at Sony AI Research, what I was able to sort of achieve, or sort of like this soft max threshold of the resources I was able to acquire. So 8H100 GPUs is I believe, a modest assumption. In deep learning, the faster you can iterate generally, faster you can innovate. So with that principle, we also defined a limit, or sort of like this 1 week soft threshold, that we want the model training to finish within this time, so that the user or like the downstream ideas or hypotheses can be tested quickly on this model. Again, even with 8H100, one can spend 40 days and train stable diffusion 1.5, but that beats the point. And finally, we did not opt to reduce the scale of our models, as when we train our models in open world setting. For example, if we take Flux or Stable Diffusion, we want these models to respond or like be able to generate images for all prompts in the open world setting that a user can potentially supply to them. So with that principle, we assume that with the model parameters still need to be fairly large to have enough expressive power to learn image generation in open world setting. So we do not change or reduce the size of our model, though it's very tempting because it would directly reduce the cost. We opted not to do so. And finally, a constraint which was in sort of like influenced by very practical reason is the size of our data sets. Now, again, similar to model size, the larger our training data sets are, the better our model is going to be. And because of that reason, it's common to use billions of images. There is a twofold challenge there. First, storing such large amount of images or just managing them itself as a huge engineering overhead and also a financial overhead. So for example, in our setup, it would require us at least 100 terabyte to process the images or like store and process the images that stable diffusion early versions have used. And second, even when we reduce the size of data set, often some of the previous works have used proprietary data sets. that are not available to the public. So we put two practical constraints here. First, we intend to train our models with data sets that are at least an order smaller than 1 billion images. And second, all images we use has to be publicly available so the community can build up on this work. At any point, if you have any question, please do ask. And with these constraints and setups out of the way, let me jump into the sort of like a preview of our key results. So here I show Stable Diffusion 1.5 and 2.1. These are the two models I'll be using as a baseline. Again, these models have been like downloaded millions of times. They are not state of the art, but they are one of the key baselines or one of the key models that the community has used. And it was a good starting point for us to consider. Here I'm testing, sort of like showing these image generation from these two models on this really common prompt of an astronaut riding a horse. And here we are ablating the style or style of the generation of these images. So on the right here, I'm showing the results from our model. The model was trained with a budget of exactly $1890. Instead of billions of images, the total images used to train this model were only 37 million. So it's not only just low economical cost, it's actually also very small amount of training images that we used. And we find that compared to SD 1.5 and 2.1, the model does achieve a better control of over image style and also a higher degree of photorealism. And near the end of my talk, once I go through the algorithmic details, I'll show more examples and even quantitative comparison between these models. And the total training time, again, to highlight here was, we set out to train our model in a week, but eventually we were able to train it in just roughly 2.5 days. So much lower than what we originally targeted. Now, to summarize the key factors that enabled us to reduce this cost, I can break them down into three big components. First is really tackling or innovating on the model architecture front. The second is the training setup, and this is something I believe would also be related to if you consider fine-tuning these models. So not just training from scratch. I think the findings there would be very relevant in fine-tuning, as someone I think in the audience highlighted that they're interested in fine-tuning also. And finally, I touched base upon some of the decisions we made in the training data set and how they helped us in training models on low scale, on low cost. So let me summarize the key findings on the architecture front. And maybe before jumping into that, I just want to give like a quick overview of sort of like the class of diffusion models we train. So whenever I'll be referring to diffusion model in my talk, I'm implicitly referring to latent diffusion models, or sort of like stable diffusion model itself is a latent stable diffusion model. So presume that we are always training a model in a latent space. And what I mean by that is that we are taking our image in the pixel space, which is like a RGB image, and passing it through an image encoder. And the encoder is compressing the image into the latent space by reducing its height by 8, width by 8, and increasing number of channels from 3 to 4. So this is like a compressed representation of the image, and there is a decoder that can decode the image. We are doing, or what as a community has also done, is you also take your text caption, for example, like a skeleton mecha with striking red, blue, like any prompt per se. And then you also compress your prompt from these text form to also sort of like this latent embedding form. So you get these two signals, your image in a latent, like as a latent signal, you get your text as a latent signal. And this is the latent space in which you train a diffusion model. So by like implicitly, we will always be sort of like training a diffusion model in the latent space. The key idea we wanted to pursue is that the cost of training any model, be it a transformer, be it a convolution neural network, is always proportional to the number of pixels the model has to process. And our objective was simply to cut down this cost. So if I'm training a diffusion model or training in per se any generative model on an image, how can we mask out some of the pixels? This is a really simple idea, and this has been actually pursued. For example, even language models are trained with masking. For example, masked language models. There, it's often used as a self-supervised task to enforce the model to like learn the underlying patterns in the signal. Here we are using masking less of sort of like this self-supervised constraint, but more of simply a trick to drop out unnecessary pixels from the image, so the network only process or only spend computation power on things that are most critical. Now, a decision sort of like one we had to make here was that masking can done be two ways. We can simply crop out a certain portion of the image, or we can just drop pixels randomly, or sort of like drop these small patches randomly. In both of them, we can reduce the number of pixels sort of like equivalently. But the trade-off is convolution neural networks, which process continuous images, can only process I hope you can see my cursor, can only process images where we do cropping. But transformers, on the other hand, give us flexibility that they can actually process both type of images, because transformer, all they need is just a sequence of patches to process. So here, even in the image where I'm dropping sort of like these patches randomly, we take the patches that are non-masked and just create a sequence out of them and pass that to the transformer. So that's one of the key reason we opted for the transformer. And in a sort of like in a few minutes, I'll also quantitatively justify this design choice. Challenge with input masking, as you can see clearly, is that as you mask more and more number of pixel, the information content in the given image goes down. So if I mask 75% and even more than like 75, it's hard even for a human to recognize what's the key object in the image, let alone learn to synthesize it. This was clearly visible if you start training diffusion models with masking. So some of the previous work have showed that if you start masking beyond 50%, the quality of generated images significantly degrades. So here the plot on the left is showing FID, which is a very common metric used to measure quality of synthetic images. So FID lower is better. So as you can see, FID goes from somewhere around 10 to close to 100, and like increase in FID from 10 to 100, almost saying that the model is completely unusable. So one of the key challenge for us to solve here was, how can we increase the amount of masking? How can we mask or drop as many number of pixels as we can while retaining performance again to the maximum extent? And the idea we opted to use was embarrassingly simple, actually. So here, if we consider like the pipeline of how an image is processed in a diffusion transformer, we first take an image, convert it to a sequence of patches. Then in naive masking, we just drop patches randomly, and then pass this sequence of patches that are not dropped to the transformer, and the transformers process it. If we, let's say, do 75% masking, we drop 3/4 of the patches, and the transformer is only spending 25% of the compute that it would have otherwise spent. But the trade-off, as you can see, is that whatever patches we drop, the semantic information of those patches from the image is completely unobserved by the transformer. The idea I was referring to earlier is that we need a module to be inserted before we do masking that can ensure that even if I'm retaining 25% of the patches, those 25% of the patches have the maximum semantic information about the original image. And this can be seen a bit more intuitively from like this style of ideas, like how attention works, for example. So if you consider like one of the key principles behind attention in transformers is that I'm taking all my input sort of like tokens or patches. I'm predicting, or I'm capturing, or in some way I'm instilling this constraints or this design that now each output will be a weighted sum of the sort of like weighted sum of the information in these individual tokens. So essentially, the patch mixer here could be a very simple attention layer where each output patch is a weighted sum of all input patches. In a sort of like, on one extreme, the patch mixer could be one attention layer. And of course, like you can, instead of one attention layer, you can also use MLPs to give the patch mixer some expressive power. So like the spectrum of design choices here naturally becomes one attention layer to a few transformer blocks. The trade-off is, the larger the patch mixer is, the more computational cost we are paying on the full sequence, because the patch mixer is processing the full sequence. So the trade-off here was, we want the patch mixer to be small enough so that it can capture the relationship of all patches, but also like not large enough that its computational cost is as large as the full transform model. So we generally strike the balance by choosing patch mixer that has a computational cost somewhere around 10 to 15% of the larger transformer model we use. Now, the second takeaway was the training setup. And here, if you look at some of the work, for example, the early work from like Berkeley and OpenAI on training diffusion models, the community starting from this idea of using UNets or like convolutional UNets, and now starting to slowly move towards like, I think a year back you would have seen a lot of hybrid version of convolutional and transformers. And I think the latest models, for example, the models powering Sora, a lot of video diffusion models, and even the image diffusion models are now based on completely transformers. Naturally, I think you would see a lot of uses of transformers in training diffusion model. And the key finding we had was, when we were training a diffusion-based transformer at scale, and when we were designing its setup and ablating all hyperparameters, the one interesting phenomena that emerged is that the design setup or the design choices for a diffusion transformers or diffusion transformer are almost identical to what you would have made in training a large language model. So effectively, like we ablated design choices, for example, on hyperparameters like learning rate, weight decay. We ablated design choices, for example, on architecture such as Swigglue, the initialization of layers, the initialization of last layer, for example, in individual transformer block. So across all these ablation, effectively, as we observe a similar trend, as high weight decay helps in LLMs, high weight decay helped in diffusion transformers. Swigglue helps in LLMs, Swigglue helps in diffusion transformer too. And effectively, eventually, our training setup looked identical to the Llama, in fact, Llama 2 training setup. And there was only one hyperparameter we found that actually had an inverse trend compared to diffusion model, which was the beta 2 parameter in the AdamW optimizer, where we found that using actually a higher beta 2 helps compared to using a lower beta 2 value in LLMs. And this might itself be a bit related to that we were training models on a shorter schedule compared to a longer schedule. You can see here quantitatively that even like compared to out of the box performance you get once you ablaze these design choices, or simply if you just take Llama 2 training setup. So if without conducting this ablation, or like a takeaway here is that if you're training diffusion transformers at scale, one of the simplest thing is to take one of the key large-scale LLMs training setup and just use that. And I think that will be very close to optimal. And evidence of this you can see in the movie gen paper from Meta that came out, where they effectively used the Llama training recipe. So I think it's a sort of like two concurrent findings that show that there's a lot of value in just simply inheriting not just transformer architecture, but the transformer training setup also when we train diffusion models. A question I sort of like want to come back to this, that in transformers, we had these two choice of masking, whether we do like a cropping style masking, which is actually being done. If you consider like super resolution models, you'll often find that, let's say, even like if you consider super resolution models trained by OpenAI, DeepMind, everyone, you would find that they often train them on crops of images to reduce the cost. And the point I want to convey here is that with transformers, it's actually a bad idea to do random cropping, because it's always better to do random masking of patches. And here is a simple ablation we ran. We ablated at this axis that in transformers, since they can process sort of like any random sequence of patches, I can drop, like on left axis, I can drop patches randomly. And on the right axis, as I go towards right, I'm increasing the size of patches. So I'm going from like a binomial style masking to more and more continuous masking. And the right axis looks like that I'm completely doing like a continuous, like a square masking. And as you can see that across these three metrics, FID lower is better, clip score higher is better. And in our constrained ablation, we find that for transformer, if you drop each patch randomly, it gives you the best generation quality across all metrics. And as you, in fact, as you increase or as you go more and more towards square masking, the quality of generated images actually decreases. So this is another takeaway I wanted to share, that when it comes to transformer, and even if you are just training models outside of this setup, it might be worthwhile to going from a random a random square cropping that we inherit from CNNs, because that's how CNNs generally do masking, to going to more of a random or a binomial patch masking style approach that actually might work better in your case. Now let's, in the final couple of minutes, let's move to the large scale training results. Again, let me know if you have any question at this point. So let me just briefly describe the full training schedule of our large scale model. The training is done in in a hierarchical fashion. Again, it's extremely common. If you look at, for example, Stable Diffusion 1.5, 2.1, and pretty much any model, it would be first trained on a smaller resolution, which generally is 256 cross 256 resolution images, and then fine tune on higher and higher resolution. We only fine tune till 512 cross 512, as it strikes this balance between cost and image quality. But of course, you can also further fine tune it on 1024 cross 1024 to generate like HD resolution images. The change we made is that at each resolution, we are first training our model with 75% masking, and to get sort of like only pay roughly one fourth of the training cost. And we are training the model with 75% masking for a lot of training steps. So here I'm training for 250K steps. And as you can see, the cost paid is close to $800 for this first step of stage one. Then we are fine tuning the model with no masking for a small number of training steps. And this was to balance out any of the artifacts, mask training that might have left, because at 75% masking, the model in none of the cases have seen the full image. So there might be still some concept or still some gaps in the model understanding of what real world images looks like. This wasn't completely necessary, as we sort of like when we did a quantitative analysis, but then there might be sort of unknown artifacts that we can miss in our quantitative analysis. So it's still a good idea, even if both qualitatively and quantitatively you don't see any artifacts. There might be unknown failure modes in the model if you only do like mask training. So with that principle, we opted to keep a small fine-tuning step with 0% masking ratio. Similarly, at 512 cross 512, we do a higher number of steps with 75% masking, and then a relatively small number of fine-tuning steps with no masking. And that in turn made our total training budget 1890, which I mentioned at the start of the talk. And the total training time on 8H100 GPUs was 2.6 days. To share a bit more, like this training was optimized, I would say, reasonably well, but certainly there is room even from a software stack. I think there is Flash Attention 3 at this point, which we didn't deploy. So there is more room to squeeze out more performance here and reduce the cost even further. Design choice that one also really helped us train these models better is choosing right training data set. So here, and our total data set of 37 million images was actually a mixture of real and synthetic images. So the real data sets are fairly common that are used in, I would say, in like academic testing, that you use conceptual captions, segment anything from meta, And we also used a small amount of text caps to teach the model about generating text and images. And now a design choice we made was that we also supply the model a lot of synthetic images from previous models. So here we are considering 11 million images from diffusion models like Stable Diffusion 1 to Excel, and then we use 4 million images from Midjourney. Using these synthetic images kind of like makes this whole pipeline a bit also like distillation of large scale models. And also at the same time, an interesting finding we had is that the synthetic image actually has a lot of artifacts. So if you, for example, from Diffusion DB, if you look at a lot of images, they have poor quality. For example, in human anatomy, our models were really bad at human anatomy for a while. And these 11 million images, they're teaching a lot of wrong concepts to the model in some way. And the sort of like the design choice in our training was, how do you use these images in a way so that you can use them in early enough to teach the model a lot about the common semantics of the image, but also not overly emphasize them so that the network end up learning the artifact in these images. In qualitative and quantitative testing, we do find that using synthetic data is actually helpful despite it having poor quality and a lot of artifacts. So here on the left, I show a model trained again with the identical setup that I showed earlier on real only images. And on the right is a model trained on real plus synthetic. So the real only model is trained on the 22 million real images, and the real plus synthetic model is trained on 22 plus 15, so total 37 million images. And even in our qualitative testing, we do did see that the model with trained with this joint data actually achieves better generations. It has a better prompt adherence and also better quality of generated images. We also conducted like a human eval study and did find that the model with real plus synthetic data actually has a higher win rate. So in particular has a 60 higher than 65% win rate, both across when we ask users to rate the quality of the generated images and the alignment of the generated image with the user prompt. And that was one decision that really helped us in keeping the number of images very small, but while also at the same time achieving higher quality generation from the model. And I think this finding can be really, I would say it's really interesting, also could be really helpful, as I think in LLM space, the community has already pivoted or already pursuing this idea of using synthetic data in training our models. And I think in diffusion model, this is one of the early examples of showing that synthetic data actually does help in training diffusion models too. Here are a few more generation from our model, and you can also find more in the model, more qualitative images in the paper and also in the appendix of the paper. Finally, just to quantitatively compare our model, which again has like roughly close to 14 to 15x lower, 15 times lower computational cost than previous state of the art. It does achieve FID score that is competitive. It does not outperform SD 1.5 and SD 2.1 in terms of FID, but it actually outperforms SD 1.5 in terms of the Geneval score. So Geneval and FID, I think, are two, I would say, common metrics that are currently used to test the model image generation quality and also the prompt adherence. In interest of time, I'm skipping more details. You can check out the paper or more sort of like related works on what these metrics capture, their shortcomings. Eventually, I think the true litmus test is releasing these models and seeing how the community find them useful. I think that would be the true test of performance. And to summarize the takeaways, I think the first one is you should use deferred masking or the masking with patch mixer for fast training runs. Even if you have a lot of compute, I believe it's a good idea to do, because you can still use this mask training as a pre-training strategy as we had used in our large scale training. The second is use high quality data. And even if you can get your hands on synthetic data, it's really helpful rather than just limiting only to real only data. And the third is use LLM's training setup, not just the architecture. And I think this, though we haven't tested it, I think this finding would be even helpful if you go not just training from scratch, but also fine tuning of diffusion transformers. And the fourth is something that I didn't spend much time on, is that you should allocate ample amount of training steps in low resolution training if you're training diffusion transformer. And this is something I learned when I was training these models, is that if you are doing this hierarchical training, do spend a lot of time training the 256 cross 256 resolution model before you switch to 512 cross 512 resolution training. And I think I'm hopeful that the cost can be reduced even further. Some of the ideas I have listed here that can be directly followed after this work. One can use rectified flows over diffusion. The software stack, as I said, our MFUs aren't really great. So the MFUs can still be pushed even further with flash attention tree, with more with fusing of even more ops. The data selection can be done even better. Again, this I would say this is first iteration of ideas on some of these design choices, and certainly I think there's room to bring the cost from 2000 close to 1000 itself. And I think the broader or our hope here is that the community will be able to build on this work even further. And I think there's room, or there is the room here to bring this movement, I would say, from 2013 to 16, 17, where a lot of innovation happened because the community in Vision was able to converge to ImageNet as this test bed, which was rigorous enough and small scale enough that the hypothesis tested on ImageNet was able to generalize. So the architectures we develop on ImageNet, they were able to generalize to even larger scale practical data sets and setups like Google training on JFD dataset. So I think the room here for the community to innovate or build is to build a test bed that is as rigorous as or as large scale as ImageNet, but while still accessible to a lot of community members, or while still accessible to train at a small scale enough so that a lot of innovation can happen on that. I think that was one of the key driving factors for us to do this work, is that can we make micro budget training of stable diffusion at this new ImageNet setup, so that the innovations we do on this scale can be translated to our real world models like Dolly or ImageNet. Sorry, Dolly or ImageN. And yeah, at this note, I would like to conclude the talk. And thanks everyone for attending. And I see there are some questions in the chat. I'll be happy to go over them.
Antonin is asking, do you keep the optimizer between different training stages or different masking ratios?
We do between 256, between the resolution itself. We do not do it between 256 to 512. I did not do a full scale ablation of it, but I did a sort of just looking at roughly close to 2000 iterations at 512. And I found that the convergence was actually slower when I was keeping the optimizer between 256 and 512. Whenever we do this masked 75% training and fine tuning, we keep the optimizer state dictionary. And when we go from 256 to 512, we do not. We only sort of resume from the checkpoint, but not the optimizer state dictionary.
Related to the multi-stage training, right? So what about the training set itself between between the two parts of stage one, you have 75% masking and then no masking? Are the same images being reused, or is it a different set of images?
I sort of my apologies. I alluded a bit towards it, but I didn't clearly explain it. So I think the sort of the trade-off that's happening, if you have the high quality data set, and if you are not concerned about cost, by all means use all images everywhere. There's no reason not to teach model about a certain image in stage one or stage two. The design choices we make here a little bit is that we have low quality data that we actually do not want the model to sort of overfit to, or not even just learn enough. So kind of want to use this. It's for example, it's the way LLMs are just trained on internet, everything from internet in pre-training, and then you sort of like fine-tune them. So the sort of like the principle is similar. I'm using the stable diffusion, so I'm using this 11 million diffusion dB images that are extremely low quality actually, and I'm only using them in stage 1. So here these 11 million images, I dropped them from stage 2, because again, I'm treating stage 1 as this pre-training component where we are just simply teaching the model about what the visual world looks like. And in stage 2, we are enforcing, so like you can treat them as like SFT version of LLMs, that I'm sort of like fine-tuning the model on the high quality data that we have.
Michael is asking, how do you choose learning rate, batch size, and weight decay?
I think now there exists the approach is sort of like even more, there is a science to ablation studies at this point. I believe it's like a new optimizer or something. I might be a bit off there. We do not follow that strategy, and certainly that could be one of the future thing to really like find these parameters in even more principled manner. I think you figure them out on small scales, and then there is sort of like a mathematical relationship on how from the small scale you translate them to your large scale model. We instead sort of like did an old school study. We take our large scale training setup, and then we consider, like, I believe in the paper we are considering 3 choices for each of them, 3 or 4. I might be a bit off. There is a paper in the appendix of the table that has all these results for each of these hyperparameters. So I think for learning rate and weight decay, we are considering the choices as like the 4 values and seeing which one of these help. For batch size, we actually keep it fixed at 2048, and this is something that I think can be updated, but it just turned out. So this is like extremely common choice of batch size that has been used in a lot of diffusion transformer paper. So we just inherited it rather than ablating it even further. But yeah, there's certainly room to explore and I think make things even better by exploring these choices.
If you wanted to fine-tune a base model on some task, like maybe like on COCO dataset, how would you go about hyperparameters?
Again, fine-tuning is a really like at this point a very broad spectrum. Let's say we are doing FF like full fine-tuning rather than LoRa. One thing is like you want to the learning rate here is decade. So we are decaying learning rate across each of these stages. So effectively, if I go from like starting point 7, like this starting point of the training in stage 1 to final, I have decayed my learning rate almost by a factor of 20. One thing is like, and this is the ablation, or this is sort of like one incentive we had was first to push the learning rate as high as we could. So we found that like our models stopped converging after we use a learning rate more than 2.4 E-4. So at least in these models, they are trained with a much higher learning rate that you would generally see in conventional diffusion transformers. Again, with the motivation that we want the model to learn fast because our training steps are fairly small compared to like a conventional training steps, which tends to be like at least more than 1 million when you train like a model like stable diffusion. I think the reason I'm sharing this is to answer your question in twofold. If you fine tune a diffusion transformer, like let's say SD3 medium, versus if you fine tune these models, because you'll find that with these models, the final learning rate at the end of the training is still fairly high. It's close to like 1 E-4. So I think you can literally start fine tuning close to that learning rate. But if you're taking a model like SD3 medium, I would recommend using a lower learning rate, at least like 5 E-5 or even lower than that. And I think you can keep like batch size and weight decay fairly close to the original value. We actually do not ablate weight decay across or do not change weight decay across each stage of training. And I think some of the other parameters that you may want to pay attention a bit more is to the gradient clip values. At higher resolution, we do use slightly higher value of gradient clipping. So if you're using a new data set and if your gradients are significantly off or significant, has a very high variance, you may want to start with a lower grad clipping value. It is a very broad question, sorry. So I might keep going on and on for a while here, but I think I would imagine that the principles of fine-tuning it would be no different than principles of fine-tuning any other large-scale models. And it's sort of like just keeping eye on the standard hyperparameters and standard reasons why fine-tuning may sort of crash at any point. But after that, I think it should be it should follow pretty much the same set of principles.
Xavier is asking, did you try to train with only synthetic images, but accounting for the difference in dataset size?
Yes. So one of the things we did, something I think we will soon, it's not out there in the public version of our paper, will be soon, is we actually wanted to understand this asymptotic behavior of synthetic data. So we actually train models. Out of my head, I don't have a number to share with exactly 22 million synthetic images. So I assume that's what the question is about. So here I have real 22 million. Can we train on 22 million synthetic images? And I would presume that model would, of course, fare poor then, because real data has, again, higher entropy, higher degree of information compared to synthetic images. And I think this is a trend you would see in a lot of places, not just in generative models, that from synthetic data, you may start learning things better at start, even faster. So if you train ImageNet model on synthetic ImageNet, you would actually converge faster, but not necessarily to a better point. And this is what we ablated by training another version of our model on 500 million synthetic images. So we really wanted to understand this asymptotic behavior, or how much synthetic data alone can improve performance. And we found that though it was, again, able to do better than this real plus synthetic model we have. And so the Geneville score of the model that was trained only on synthetic images, only on 500 million synthetic images. So really kind of try to push synthetic data to its limit. The Geneville score improved from 0.46 to 0.52, and FID also slightly improved. The synthetic data, essentially the TLDR of what I'm trying to summarize here, is that synthetic data, though it's helpful, it has a very limiting behavior, or it has its diminishing return. And I think once you combine it with real data, you sort of get best of both worlds. But at certain point, I think even in low cost training setup, there is only limiting information that the synthetic data is able to provide from us, or is able to provide to us. And I think after a while, once you take advantage of that, once you sort of get to Geneville score of 0.52 from synthetic data alone, you really have to improve the quality of your real data if you want to improve the model beyond that. But yes, synthetic data across tasks has this interesting behavior that you can actually learn faster from it, but may not necessarily better if you just use synthetic data. And if you combine real plus synthetic, both in training discriminative models and generative models, you end up having this benefit of having best of both worlds.
What is the ratio should be?
I think the ratio generally, I would say, depends a bit on the task. I think 1-to-1 really would make a lot of sense, because essentially you want to spend a lot of time or a lot of steps on the real data itself. So if I combine 20 million real and 500 million synthetic images, I think I'm not weighting my real data enough in the training. So I think at that point, maybe the training can be done maybe a bit more in the sense of continual learning, that you can just train on synthetic first and fine tune on real. So you do not have to run into this issue that your synthetic and real data are not weighted equally. But I think if you're mixing them, it would make sense to keep the ratio fairly somewhere in below at least 1-to-2 or something, so that you are seeing real data enough in training. Otherwise, you are kind of limiting yourself, or kind of running into this asymptotic behavior of synthetic data if the model is predominantly only trained on synthetic data.
Thank you for the presentation. Just I'm curious, the work focused on creating strategies for masking the data to reduce the computational requirements. Have you played around with more on the algorithmic side, where you look at the denoising process, and in particular looking at the noise schedule used during training. So then you could, let's say, spend more time at the early or at the larger noise stages, and then spend less time on the smaller noise scales, so you can kind of maybe learn semantic features early on and so on and so forth. So I'm just curious if you've thought about that, and that's kind of like a different paradigm that traditional, let's say, DTPM and other techniques were exploring from the diffusion side of things. And then if I could just throw in a quick second question is like, what is the motivation for, let's say, going from scratch, let's say fine tuning on a budget, or like training from scratch to under $2,000 versus, let's say, I just wanted to fine tune the diffusion model? What are your understanding of the pros and cons and the use cases for either or?
Great questions. So yeah, let me engage into each of them one by one. So to answer your first, yes, we do ablate this design choice. It's a really compelling design choice to ablate. So we are using EDM training setup from NVIDIA. It's a very, like, I would say, very unified way of looking at diffusion models. And we do change the sort of like the sort of like mean and standard deviation of the sampling distribution. So it determines how high, or sort of like how large are the noise values that you predominantly focus on training. And I think there was, and again, this is ablation. I think so you can check this out. It's in our ablation studies in the appendix. There is a big table where we sort of like consider 4 values of this. So I think we do find this trade-off, and this is aligns with the study that sort of like a stability AI did in their SD3 paper, where they moved to flow-based models. Is that often I think you should choose high noise values, but not really high ones. And again, this is empirical results, so I think it's very hard to answer why exactly. I think I actually don't remember the numbers, but I think it was mean was minus 0.5 for the log normal distribution, and standard deviation was 1.2. That worked out really well. I think you might have choose standard deviation 1.1. That might have been like almost as good or slightly better or worse. But I think if you do like a coarse grain ablation study, and if you choose like one log normal distribution that samples really high noise values, and one that focus on like a really small noise value, we often found that somewhere in between the two works best. And this is sort of like a U style curve that you observe. And I think this sort of agrees with what some of the other previous works have also observed when you train with different noise schedules on scale. And to answer your second question, the motivation behind this work, and this is a bit connected to like what I shared in the last slide, I think it was less of I think it was less of building or like fine-tuning models, because I think Laura does a great job at that. And like fine-tuning ecosystem is like I think it's matured enough. The motivation wasn't just the community to like take these models and just fine-tune them and just like tweak them or like customize them, but rather the motivation was to actually take or sort of like some of my work actually focuses on showing that our models, even though they are much better than what we had 5-10 years ago, has a lot of failure modes. So vision actually hasn't been solved, and far from being solved, it's not even close to where we are in LLMs or where we were in LLMs like a year ago. Even if you take the latest flux models, if you increase the complexity of your prompts, you'd see that there are a lot of issues or failure modes in the model generation. If you take images from these models, for example, most of the images end up having this plastic effect. There is a high degree of smoothness in our generations, exception some of these like flux images that the community has showed. So I think the objective was to create a test bed where you are imitating the setup of a large scale model, because effectively the objective is to test hypothesis. It's like Anthropic building like a big Opus model, but they built Sonnet first because they wanted to test early ideas and everything on that. So this is like building Sonnet for like a small scale training setup for something like GDM, like Google DeepMind doing like gamma models and informing design choices or testing hypotheses on there for the bigger Gemini model. This is a small scale test bed, but it has to be trained from scratch, and it has to be trained in a nearly identical way for our large scale models. So and we can ensure that, again, and this is a test of time for this work, that would hypothesis tested on microdiffusion would translate the way things translated from ImageNet to broader vision research.
Are you guys now training a large-scale model?
So I think that's one of the big compute challenge we run into. So I think this was close to a bit max scale. We are looking a bit into video models and trying to scale things up there. But I think in vision, what we are branching out is more like breadth first search. So we are looking at a lot of ideas that were previously inaccessible to us. For example, private training of diffusion models at scale, looking into ablating, like understanding influence of data in training at scale, because since now we have only 2.5 days runtime, we can quickly churn out ideas. So I think it's more like a breadth first search we are doing compared to training an even larger scale model, because smaller scale works for us because it gives us faster iteration cycle.
Is this work open source, available on GitHub?
The paper is available. The models aren't yet. I can promise that they will be out soon after the CPR deadline, certainly.
So it will be available on GitHub.
Yes, we will certainly make them available. They are still, I would say, kind of like in the process. We have approvals and everything sorted out. So there is no reason for them to be public. It's just a matter of time.
Can you please share that link when it's available, so I share with the community?
Yeah,
because
I'll
many
certainly
people
share
would be
that.
interested.
There is a placeholder repo that I created. I think that's public. I'll share that already, and the code will be pushed on that repo.
Yeah, sorry, great PowerPoint, really interesting stuff. And not my expertise. I usually deal with a lot of language models, but nonetheless, this is still very fascinating stuff. And my question is in regards to the high mask ratio. Perhaps I'm misunderstanding something here, but I thought you mentioned earlier in your PowerPoint that a higher mask ratio led to lower performance.
Yes, it does, because I think it's a balancing act. You factually want to push the masking ratio to the point where you can retain performance as much as you can, because the higher the masking, the more you save on computational cost. But at the same time, if you degrade performance, you pay in terms of the quality of your generations. So here, I think I can justify like the design choice of 75% a bit, that if you consider the red curve, which is our model, I'm on x-axis increasing the masking ratio, and on y-axis we are considering these three metrics: FID, clip model based FID, and clip score. FID lower is better, clip score higher is better. And I think with 75%, at least again, the incentive is to push it to the max as much as we can, and from that FID, like up to 50%, we saw like really strong stability in both in FID, clip FID, and FID clip score. But till 75%, we sort of like felt that it was a balance, that the FID scores weren't degraded a lot, certainly significantly lower than the degradation that happens in previous techniques. But also at the same time, it is giving us like another factor of improvement, or 50% masking ratio. And I think we also tried training models with 87.5% masking ratio. And I think at that point, even qualitatively, even qualitatively, when we analyzed, the generation quality was fairly bad. That's how sort of like we landed at this like a balancing design or balancing choice of 75% masking.
This may be a bit naive. Was there augmentation involved in this as well through the training process?
There is some literature, a bit in the GANs from NVIDIA, that try to train the models with augmentation. But I think as we move more towards open world and training models on millions of images, I think that sort of like got phased out, because that was more like, how do you train on CFAR or ImageNet with some augmentation, because you don't want the model to end up learning the augmented distribution. In fact, we don't even do horizontal flipping when we are training the model on sort of like these web scale 37 million images. Web collected 37 million images, because even with the horizontal scaling, you can mess up the text in the images if you just flip the image. So there is literally no, like you can do random cropping, but even that has its own artifacts in the generation. So I think in vision side, at least in generative models, augmentations have slightly phased out. And I think you sort of you can use them. For example, you do random cropping when you train models that it can generate sort of like varying resolution images. So if you go to like SD3 XL or any model after that, they can generate like varying resolution images, but that is trained in a way, or like you sort of like give the model the information about that, hey, I'm taking this resolution image, or I'm taking a crop of this resolution, and you condition the model on that. So that's like, I would say, a slightly product oriented design choice. Like you are not, like in some way you are not trying the model to use augmentation, but asking it to sort of like add this new cool capability so that it can handle varying resolution image. But again, from a simplified setup, we felt that was a bit out of scope, because it's not necessarily like a fundamental capability, but more of like it's a usability style design choice. But you can also do that. It is a fairly straightforward thing to add. It just makes that training more messy. You can your batch, like your data loader, has to be slightly tweaked to handle those variations.
Interesting. Thank you so much.
Let's take last question and wrap up. I've been here like for a while. I see Michael. Have you tried any quantization methods to do training or inference?
No, we just do mixed precision training. We do not pursue quantization like post training. Again, I believe those things certainly can be done, as they have been done with previous models. But the objective wasn't really, this is not a production grade model by any means. We did not sort of like push to pursue that direction.
But do you think it could become production grade model?
I think you should always use Flux or something. It's a good model. It's as I said, it's like Gamma model for Gemini, or Sonnet for Cloudy Opus model. It's a good model to test early ideas. So it's a good thing to test crazy ideas on, but not something you want to put in your product pipeline.